Hey there! In this lecture we're going to start about unsupervised learning, which is also a branch of machine learning. After supervised learning, we will learn about unsupervised learning. So the roadmap for this section will be, we'll learn about the basic concepts, then we'll learn about k-means algorithm. Moving on, we will learn how to represent different clusters. We will learn hierarchical clustering, distance functions, data standardization, handling mixed attributes. Then we need to come up with the metric-based evaluation to understand which clustering algorithm to use in which problem. We will learn about cluster evaluation and discovering holes in data regions. In the end, we're going to summarize everything. So let's start with comparing supervised learning and unsupervised learning. We have already seen supervised learning in action, and we have seen how we can use linear regression and logistic regression to do that. So supervised learning is basically discovering patterns in a data that relate data attributes to the target class attribute. So whenever we are solving supervised learning problems, we always have a labeled data set. We always have a class attribute. We always have a target value, which is the actual predicted value, on which we often fit our problem to get a better understanding, to get better sense of the pattern of data. So these patterns are then utilized to predict the values of the target attribute in future data instances. So after that, we have trained our model on a labeled dataset. Then we can use it to predict target attributes in future data instances which the model has never seen. On the contrary, unsupervised learning is used when the data has no target attribute, especially when the dataset is not labeled. So the question is, if you do not have a target attribute, you do not have the required supervision to make your model learn anything. So then if you want to explore the data, you have to find some intrinsic structures in them, and you need to explore them on your own without any external supervision. So clustering is one of the methods to understand and explore those intrinsic structures. Clustering is a technique for finding similarity groups in data, which are ultimately called clusters. So what clustering does is it groups data instances that are similar to each other. And so what clustering does is it groups data instances that are similar to each other in one cluster and data instances that are very different from each other into different clusters. So it is often called as an unsupervised learning task, as no class values denoting grouping method or a grouping label is given. So which is not the case in supervised learning. Due to historical reasons, clustering is often considered synonymous with unsupervised learning. In fact, association rule mining is also unsupervised. So we're going to focus on clustering in this particular section, and we're going to talk about clustering a lot. Okay, so let's move on. An illustration of what we just studied about clustering algorithm is the basic and core functionality of the algorithm itself. So if you want to visualize it, you can understand this by looking at this particular grid. You can see that there are different points that are grouped together into three different clusters. So the only particular intrinsic characteristic of each data point in a cluster is that they are quite close to each other. Each data point in a cluster has very less distance between them, which is the key interesting feature used by clustering, enabling it to put them together. So the question is, what is clustering for? Where can you actually apply clustering or unsupervised learning in real life example? So example one is especially, let's talk about grouping people of similar sizes together to make three different sizes of shirts. Tailor-made shirts for each person will be ultimately too expensive, and one size fits all does not fit all the people. So you need to divide the sizes into three different categories, and putting people into these three different categories, clustering algorithm can be the most efficient one. So you take the dimensions of people, of their body structure, and you put that data into the clustering algorithm, and it's going to cluster those body structures that are small, medium, or large. But the important thing here is that we do not have these labels. It's just going to give us different clusters. But these clusters will have some property that as you can see in the above example, the cluster on the extreme left shows that the X and Y values were smaller for this cluster. And on the extreme right, you can see that the X values were larger, but the Y values were smaller. So when after the clustering algorithm will cluster the body structure information into different clusters, then we can understand which cluster will represent small, medium, and large. So that is quite smart, but the clustering algorithm does not know information about small, medium, or large. So let's talk about another example. In marketing, customers are often grouped together according to their likes, dislikes, and preferences. Especially, I do usually give an example of the Netflix. Netflix actually gives you preferences according to the movies you've watched. So if you're watching a lot of thriller movies, you will see a lot of thriller movies on your homepage, which tells us what it does is it uses the clustering algorithm. It takes your information about the movies you've watched and understand, okay, the movie A he watched is closest to the movie B, which also has similar characteristics because they're both thrillers. So Netflix also uses the same segmenting of these marketing strategies using clustering algorithm to do customer targeting, and a lot of marketing agencies use the same technique as well. So another example will be if you want to organize a lot of text documents, then the best way to do that it will be to organize them and group them according to their content similarity. So that is another application of clustering. So the thing is that clustering is one of the most utilized data mining techniques. It has a long history and it is used in almost every field: medicine, psychology, botany, sociology, biology, archaeology, marketing, insurance, libraries, etc., etc. In recent years, due to the rapid increase of online documents, text clustering becomes very important. So let's talk about the aspects of clustering. A clustering algorithm can be used in different ways, and different types of clustering can also be categorized into different types of clustering algorithms. So we have partitional clustering, hierarchical clustering, and a distance function clustering quality which actually defines these different types of clustering. Inter-cluster distance is maximized, and in the other one the intra-cluster distance is minimized. So in order to understand this, the inter-cluster distance means that given a particular cluster, the data points within that cluster should have minimum distance between them. And the intra-cluster distance minimized is to do that different clusters should have maximum distance between them. So the quality of a clustering result depends on the algorithm, the distance function, and the application. These are the two aspects, the distance function and the application. So let's talk about the most popular clustering algorithm, the k-means algorithm. So k-means clustering is a partitional clustering algorithm. What it does is that it takes the data points of instances, let them be x1, x2 up till xn, and it puts them into a vector. After that, we call it the real valued space because all the data points are real numbers. So this is also represents the dimensional attributes in the data. The k-mean algorithm partitions the given data into k clusters. So the k comes from the number of clusters. So each cluster has a cluster center called centroid, and k is specified by the user. So we will understand how the k-means algorithm works. So what does k-means does is that given k, the k-mean algorithm, what it does is it randomly chooses the k data points, which ultimately call them as seeds, to be the initial centroid cluster centers. Okay, so it selects particular as random data points and it assigns them to centroids. So then it assigns each data point to the closest centroid. Okay, so imagine that you take random data points and consider them to be centroids, and then you measure the distance from the centroid to all of the other data points. After that, you've computed the distance from the centroids. You will assign those data points which have the closest distance, which have the minimum distance, to the centroid, and then you can assign them to that particular cluster. And then you will continue to do that until the convergence criteria is not met. So, and you will continue to do that. You will continue to assign each data point to the closest centroid, and then you will recompute the centroids using the center cluster membership. So when you've assigned, you see that the status of centroids will ultimately change, because at the first step you will select them randomly, but after the second step you will recompute the centroid locations, because then you will have different data points that will have be closest to the entire given to a certain cluster. Okay, so let's look this into a different way. Let's look at the mathematical annotation for this. So the algorithm for that, it is chooses k data points as initial centroids. For each data point, it computes the distance from x to each centroid. Okay, so we take all the data points, we compute the distance from to their centroids, and then we assign x to the closest centroid. That is the first for loop for that. Then after that, we recompute the centroids using the current cluster memberships. Okay, so since we have assigned the x to the closest centroid, then we will recompute the centroid using that one would be the center for that. So after recomputing the centroids, we will continue this, repeat this until the stopping criterion is met, and we will see what is the stopping criterion. The stopping or convergence criterion is basically when there is no reassignments of data points to different clusters. So after a certain point, you will realize that reassigning of data points to different clusters will stop. The other point will be that no change of centroid or minimum decrease in the sum of squared error. So the reassigning of centroids will stop, and which will be the second stopping or convergence criterion. And you can see that this SSE, which is the sum of squared error, will be decreased to a minimum. Okay, so that is similar to the, you can say that this change of centroid will stop. So centroid allocation or assigning is basically that particular data instance that has, you can say, closest or on an average of the minimum average distance among all the data points in a particular cluster. So that's why how we assign this centroid. So when it says that it stops assigning centroids, it's basically that there is no further decrease in the sum of squared errors. So the equation of SSE is given in this, and it's not that mathematical. It's basically what it's doing is just that it given the k clusters, it's going to measure the distance between x and the centroid. J is the centroid, j is the jth cluster, and Cj is the mean vector of all the data points. So an example, visual example would be randomly selection of k centers, then we will cluster them, and then we will continue to recompute the centroids. The centroid location changes in the C diagram, and then we will initially move into a better centroid location, and then we will continue to do that until there is no further change in the minimum distance. So let's talk about the distance function, which is used to compute the distance between the centroid and all the data points. So let's look at the distance function which is used to calculate the distance between the centroid and the data points. We're going to use the Euclidean space, which will be the mean of a cluster is computed with. So what we're doing here is that we're computing that where the mean can be defined and computed. Okay, so let's talk about the distance function. So the thing about the k-means algorithm is that it can be used for any application dataset where the mean can be defined and computed. Okay, so wherever you can use it, anywhere where there is a mean and can be defined and computed. Okay, so in the Euclidean space, the mean of a cluster is computed by this formula. We are going to sum all these values. We're going to divide it by the number of data points in the particular cluster, and then we're going to calculate the distance from one data point to a mean, which is the centroid, using this distance function. So we are taking each data point, subtracting it with the mean, and taking the squared value, and then we're going to sum all these squared differences, and then we're going to take the square root, which is the distance calculation. A disk version of k-means. Let's talk about this. Okay, so the k-means can be implemented with data on disk. Okay, so in each iteration, it scans data once. As the centroids can be computed incrementally, it can be used to cluster large datasets and did not fit in main memory. Okay, that is quite important, and it is really beneficial, especially when you have a lot of datasets and you do not need. It becomes quite difficult when you have to store them in your memory, in your RAM. So the thing we need to control over here is the number of iterations. In practice, it is less than 50. But it is not the best method. There are other methods like bridge or like scale-up algorithms, like bridge is one of them. So the disk k-means does is it can it can work on the data. You do not need to store the data points on your main memory. That's the number one point. And it can perform operations on the data on disk. And secondly, it does not need to, you can control the number of iterations. So let's talk about the pros and cons of k-means. The strengths, or you can say the simple strengths of k-means, is that it's easy to understand and to implement. That's linear. You can say the time complexity is linear. It's not squared. So it has a time complexity of OTKN. T is the number of iterations, K is the number of clusters, and N is the number of data points. So both K and T are small, and k-means is considered to be a linear algorithm. K-means is the most popular clustering algorithm, so you can say that it is used by everyone and anyone whenever a clustering function is performed. So important note about k-means is that it terminates at a local optimum if SCE is used. So the global optimum is hard to find due to complexity. So the local optimum and global optimum is a more of a machine learning term. Whenever we are learning, training an algorithm, we try our best that the algorithm converges to the global optimum. But sometimes the algorithm gets stuck at local optimum and it terminates over there, which is quite popular, especially when we have a lot of complex data with a very high dimensional space. And k-means suffers from this problem as well, and especially if the SSE, sum of squared errors function, is used. So the weakness of k-means is that it is only applicable if the mean is defined. And there is the type of data in which the mean cannot be defined is the categorical data. So the centroid in that type of data will actually be represented by the most frequent value. So that is the problem of k-means. It cannot be applied to categorical data. And there is another problem, is that the k over here is a hyperparameter. The hyperparameter means that it has to be specified by the user. You cannot learn it. So different k values can lead to different results, which can cause confusion. So since this algorithm is based on the mean, is highly dependent on the mean, since the centroid calculation is based on the mean. So what does is that we all know that mean is highly affected by outliers. So the algorithm is also sensitive to outliers. We all know that outliers are data points very far away from other data points. Outliers could be errors in the data recording or some special data points with very different values. So what we know that outliers are alien values that are present in our data, which have some features that alienate them, differentiate them from all the other data points. So let's visualize what we have learned about the outliers. If there is an outlier, then this will be the problem of the clusters. So this is not a proper cluster if there is an outlier. So the ideal cluster would be that if you were somehow able to ignore the outlier, and this would be the ideal cluster. Okay, so this is the problem when we introduce outliers into the k-means algorithm. So the workaround to the outliers is that we can do some pre-processing and remove all the outliers by identifying them and then remove them. Okay, so we can just remove those pre-processing to get that done, but that would be costly. So what we do is we remove some data points in the clustering process itself, which are much further away from the centroids than other data points. Okay, so then we can categorize those data points as outliers. So to be safe, we may want to monitor these possible outliers over a few iterations and then decide to remove them. So we select an outlier after we have completed a couple of iterations so that we are sure about it, that this is actually an outlier. So another method is to perform random sampling. Since in sampling we only choose a small subset of data points, the chance of selecting an outlier is very small. So this is very logical, simple way to remove outliers. Okay, so we just select a small data set to avoid getting into the outlier situation. So assigning the rest of the data points to the clusters by distance or similarity comparison or classification remains the same, but we take a small data set. The first method, like I said, is that we can identify outliers before we get into the k-means algorithm, and then we can remove them, so it won't cause any problem. So this is another example of, you can say, the smaller sample sets. Okay, so another weakness of k-means is that it is very sensitive to initial seeds. Do you remember the first step of the algorithm is that it selects random centroids? Okay, so if it is somehow selects some centroids that are not ideal enough, then it will take a lot of iterations to get to the local optimum. So this is another weakness of k-means. It is very similar, sensitive to the initial seeds. So if we use different seeds, then we can get good results. This is an example that if we select randomly and select bad seeds, then we can ultimately lead to poor results. So there are some methods we can use to help choose good seeds. So we can use them as well. Another thing is that the k-means algorithm is not suitable for discovering clusters that are not hyper ellipsoids or hyperspheres. Okay, so in this particular example, these clusters are not hyperspheres. Okay, so it will be a problem for the k-means to identify them, because this cluster is forming a crescent, a clockwise crescent. So this is not a hypersphere or a hyperellipsoid. So it will not be accurately you can say it will not accurately cluster this. So this is one of the another weaknesses of k-means.